Good evening, friends. Welcome to the session. So we were continuing with domain analytics on the topic energy and resources analytics. So from today, we'll be starting with the model building part. Model building. Or also we can call it as data mining step in CRISP ML. So this data mining again, if we talk about data mining, it can be broadly divided into three major parts. One is supervised learning. Second one is unsupervised learning. And third one is an advanced concept, that is reinforcement learning. So in supervised learning, we have a data set which we first divide into two parts, basically using simple random sampling. This first part is known as training data. Second part is known as test data or validation set, we can say. On this training data, we will use some ML models. We'll use some ML models to get a mathematical equation. Okay. And using this mathematical equation again, we will test on this test data to give prediction. And this prediction will be known as outcome. Okay, so this is supervised learning. Then next we are having unsupervised. So this is known as supervised, first one, because we are doing a training phase. This is the supervision phase. Supervision phase. So here we are supervising using the training data to get this mathematical equation. Now, unsupervised learning. Okay, in this there is no training phase. Okay, supervised, there is a training phase. Here there is no training phase. Also in supervised, we try to find the relation between input and output. So here output is known. In supervised learning, output is known. In unsupervised learning, there is no output, or output is unknown. Okay, here the output values are unknown, or the output variable is unknown. In this, what happens? We are having a data set. From this data set, we'll apply some ML algorithm on this data set. Okay, to get our patterns. Okay, which can by which we can group this data into different groups, or also known as clusters. Okay, so here natural clusters can be formed using patterns. Okay, so there are many different formulas using which we can do this grouping or clustering. Here we can find the natural groups in the data set. Last is reinforcement learning. Okay, reinforcement learning. In this, we create an agent and we put them in an environment. Okay, put them in an environment and we see how does this agent reacts to this environment. Okay, and if this agent it does something which we require it to do, we will give it some rewards. Okay, this is one of the forms of teaching this. We can say this agent. Okay, we'll give it some rewards. This is also known as positive reinforcement learning. Okay, we are doing positive reinforcement. There is another method by which we will penalize it. This is known as negative reinforcement learning. Okay, so these are the various data mining concepts: supervised, unsupervised, and reinforcement. We'll be dealing with today unsupervised learning technique, and in this particularly we'll see K-means. Okay, now this unsupervised learning technique, we have many techniques. One of them is clustering. In this clustering also there are many techniques. We are having hierarchical clustering, we are having non-hierarchical, and many more. So unsupervised learning, K-means clustering, is a part of non-hierarchical clustering. Non-hierarchical. Okay, and also it is also known as a partition-based clustering. Okay, because we try to make partitions within the data set, within the data. Okay, so let's see what we'll be learning today. So what is unsupervised learning? We'll be learning what is clustering, what is K-means clustering, what are the advantages of K-means clustering, what are the limitations, what are some of the key concepts, and a use case. Okay. Next, unsupervised learning. How do we do this unsupervised learning? Let us learn here. So, which I gave you, that was a simple example. Here we can elaborate it more. So you can see here, in unsupervised learning, we are having a historical data. We put this historical data through a machine learning algorithm, ML algorithm. Okay, and we find the rules and patterns that are present in the dataset itself. Okay, natural rules and patterns are there. Okay, this rules and patterns we'll be using later. Now, suppose a new data comes up. Okay, a new data comes up which is not part of this historical data. Now we need to predict using this rules and patterns, where does this data belong to? Okay, in which category? So using this rules and patterns, we have divided our data. We have segmented our data into multiple groups. Now, this new data, where does this belong? Does this belong to this group or this group or this group? Suppose this is group 1, group 2, or group 3. Okay, we will decide using this rules and patterns by which we segregated these data. Okay, again we'll apply the same rule on this new data, and we'll do using these rules and patterns, we'll do the prediction, and from that we'll get the outcome for this new data, whether it belongs to group 1, group 2, or group 3. Suppose it belongs to group 2, it will be put in this group. Okay, so there are multiple methods by which this can be grouped under one of them, and the simplest one is using distance formula. So we'll be learning about this. Okay, so unsupervised learning, what it is, let us learn. Unsupervised learning is a machine learning technique in which models are not supervised using a training dataset. So there is no training phase here. Okay, as there is no training phase, our models are not supervised. There is no supervision here. Models are not supervised, hence the name unsupervised learning method. Okay, instead the models themselves find hidden patterns and insights from the given data. So within this data only, we will find which data are related to which data. Okay. So we will try to find which data are closer to each other. Whichever data are closer to each other, if we are talking about distance, as I told you, we'll group them together. Okay, the closer ones, we'll group them together. Okay, it can be compared to learning which takes place in a human brain while learning new things. Okay, and the goal of unsupervised learning is to find the underlying structure of the data set. Okay, so within this data set only, whichever rules and patterns are present already, we try to find that out. Okay, then group the data according to their similarities. How similar are these two? How similar are these two? If these are more similar than others, we'll group them. Okay, and then represent the data in a compressed format. So by grouping, we are forming three groups now, suppose, from this data set. These three groups can act as individual data frames. So our data is also reduced here. Data is reduced. Now this resultant groups or clusters will have low variance. Okay. They will have lower variance. Lower variance. Why do they have lower variance? So let us talk about that. So what happens when we form clusters? Okay, when we are forming clusters, suppose this is the centroid, the data points which are closer to this centroid only will be here. Okay, the data points which are far away will not be here. So what is variance? Variance is nothing but it is the distance of the data points from our centroid. Let us take centroid as mu. So xi minus mu whole square is our variance. Okay. So if all the data points are closer to each other, the variance will be minimized. If this point is also taken, then we'll have a greater variance. But as these points are not taken, variance will be minimized. Okay, so you can also say that this clustering technique or k-means clustering mainly, we can say these are all minimization techniques. We try to minimize the variance. Okay, so if we just draw the scatter plot of this. So if you remember, we discussed already scatter plot. Scatter plot is a bivariate analysis. It is a bivariate analysis. In this, we are having two variables, V1 and V2. Suppose these are the two variables we are having here, V1 and V2. Suppose this V1 and V2, when we do the scatter plot, okay, so generally in scatter plot, we can find the correlation. But we can also find the clusters. Okay, so suppose this kind of data it gave us. So we can see that these data are closer, these data are closer, and these are also closer. So what we can do is we can cluster them together. Okay, using k-means we can cluster them together. Now, what is k-means clustering? Let us see. non-hierarchical clustering. Also known as partition-based clustering. Okay. Now in this K means clustering. It is a partition-based clustering. So it is also an unsupervised learning method. So it is one such unsupervised learning method that aims to group similar data points together. How to find this similar? What is this similar? Similar is nothing but if two data points are having lowest distance among each other. Lowest distance. So similarity is a comparison, you can say. If we suppose have three records, suppose 1, 2, 3. In this 3 record, I want to find if record 1 is similar to record 2 or record 1 is similar to record 3, which is more similar, 1 to 2 or 1 to 3. We are trying to find out. Okay, so the distance, here we measure the distance to find the similarity. Distance between 1 and 3 suppose is 30. Between 1 and 2 is suppose 20. So we can say that is more similar to 2. One more similar to 2. Just a second. Yeah. So 1 is more similar to 2. We can say because the distance between 1 and 2 is lower than distance between 1 and 3. So we can cluster now 1 and 2 together. Okay. Like this. So we'll group similar data points together in a cluster. It allows us to cluster the data into different groups, and it is a convenient way to discover categories of groups in the unlabeled data set. Okay. So this is an unlabeled data set on its own without any need of training. So there is no training step involved in this. We can, from an unlabeled data set, we can find groups. Now, this is also a centroid based algorithm. Okay. So we can see from the name only, it is K-means. Means is centroid, you can see. It is a centroid based algorithm where each cluster is associated with a centroid value. Okay, the main aim of this algorithm is to minimize the distance from a data point to their corresponding cluster centroids. Okay. So let me tell you more about this. So we are having K-means. Okay, this name only tells us many things. K is the number of clusters to be formed. We'll have to decide this beforehand only. It is the number of clusters to be formed. And it is means because we are using mean of all the data points in a cluster. Mean of all data points in a cluster means it is the arithmetic means, which is the centroid. We find centroid of each cluster every time it accepts a data point. Every time it is accepting a data point, suppose it is accepting this, again the whole thing's centroid will be calculated. Suppose it is previously here. When we accepted this, suppose it shifts here. Okay. So every time we accept a data point, this centroid will change. So we'll be discussing how this functions. Okay, so let us discuss this functioning of K means clustering. So in this K means clustering, we will initialize the centroids, K centroids. Okay. So we'll first of all decide the value of K. This has to be decided beforehand. Then for each sample in the set of samples, we will assign closest cluster K. Okay, based on Euclidean distance. So what it means that suppose if we are having this kind of, let me use straight lines. Yeah. Suppose I'm having data points like this. Okay, so first of all, we'll decide the K centroids. First of all, we'll decide K value. Suppose I decided K value to be 2. K is 2. So then we will decide 2 centroid values. Out of these data points, we'll decide 2 centroid values. Suppose I decided this. This is my centroid and this is also my centroid. Now we'll find the distances of all the points from these 2 centroids. Okay. And whichever data point is closest to the centroid, whichever data point is closest to the centroid, it will be clustered together. Suppose these 2 cluster together, these 2 clustered together. Now after clustering, what will happen? Again, this will calculate the centroid. So basically the mean of these 2 values. Okay. So suppose it comes out to be here in the middle. Here also in the middle, suppose. Again, from the centroid, okay, all the data points distances will be calculated. Again, the closest one will be again clustered. Again, the data point shifts. Here also same thing. Again, data point shifts. Okay, like this until we are covering all the data points, we will be doing this clustering. Okay, this thing will be repeated again and again until we get the we reach a stopping criterion. Okay, so we'll be discussing the stopping criterion also. Okay, so initialize K centroids. Okay, then for each sample in the set of samples, we need to assign a sample to the closest cluster K based on Euclidean distance. Okay, so distances we are measuring based on Euclidean. We can use any distance formula we want. Okay, we can use Euclidean, we can use Manhattan, Mahalanobis, even cosine distance we can use. Now for each cluster in the set of cluster, we'll recalculate the cluster centroid as we already discussed. Okay, based on the mean of the samples in the cluster. And this steps will be repeated until a stopping criterion is fulfilled. We'll be discussing about this. Now, we'll have to determine the variance of each cluster and the sum of squared errors. SSE is sum of squared errors. Okay. Now this 5 steps will be repeated with different initialization. Different initialization means previously okay, we initialize this 2 red values. Instead of this, what we will do? We'll not initialize this. We'll initialize somewhere else. Suppose I initialized here and here. Then again we'll cluster. Okay, so with different initialization, we will again do the clustering and try to find. Okay, so this is done because this is a minimization technique. And minimization techniques have a fault. Okay, they often find a local minima point. Okay, so if suppose this is our curve, this is a minima, this is also a minimum. This is a local minimum. This is a global minimum. Our main aim is to find the global minimum. But suppose we start here, we are starting from here, we will reach this point and we will say that this is the minima point. Okay, it will not move anywhere else. So by initializing it with different locations, suppose if we reach here, then we can find this global minimum. Okay, hence we need to do this initialization again and again. Now, advantages of k-means clustering. What are the different or various advantages of k-means clustering? Let us know. Okay, so the k-means clustering algorithm, it is used to group unlabeled data sets into clusters based on similar attributes. So the similar attributes we calculate using the distance formula. Okay, and it is the most used clustering method because it is computationally very inexpensive. Okay, it is a very fast method and it is computationally very inexpensive. It can also scale well with large data, large amount of data. If you are having, k-means is the go-to formula for clustering. Okay, and it is also an appropriate method when the number of clusters to be drawn is known. Okay, number of clusters, if we know, it is the best method to be used if number of clusters is known. Okay, so these are few of the advantages of k-means clustering. Also speed, I already told you about this. So limitations, what are the limitations in k-means clustering? Yeah. What are the limitations in k-means clustering? So the one of the problems is number of clusters has to be chosen upfront. Okay, k value has to be chosen upfront. If this k value is chosen wrong, clusters will not be formed correctly. Clusters not formed correctly. If clusters are not formed correctly, the cluster will have no meaning. Okay, we cannot derive any meaning from these clusters. Okay. Now, outliers. Outliers have very strong influence on the results because we are finding the means or the centroid value. And as we know, centroid value or mean value is affected by outliers. Hence, we cannot use this, k-means clustering. So there are many solutions for this. We can either use k median or k medoids. Okay, one of these methods can also be used. Now, initial centroid positions, they have a strong influence on the result. Okay, so whichever cluster position we are discussing, this will have a strong influence on the result. If this is not chosen correctly, your clusters will not be formed correctly. Okay, and it does not cluster well with clusters of varying size and density. Okay, if we are having clusters with varying size or density, varying density, k-means is not a good measure. Okay, so we can use many other clustering methods are there we can use, but clustering with k-means will not be a good solution for these kind of problems. Okay, now let us learn some of the key concepts which we should remember while doing k-means clustering. Okay, so first of all, we should know that for stability, we should learn the we should run the k-means clustering multiple times. Okay, and each of these times we run, it is known as an iteration, and this all the iterations should be run with a different value of k. Okay, so with a different value of k, you should run the k-means clustering multiple times. This will solve two problems. One is initialization, and second one is local minima problem. Okay. Yeah. Then we might also find this infinite oscillating point. Okay, a data point that might keep oscillating between two clusters in each run of this iteration. In each iteration, it will move from one cluster to another cluster, then this cluster to this. It will keep on jumping in each of the cluster. So we are not able to decide in which cluster this data point might belong. Okay, so the algorithm might enter an infinite loop due to this case. So what to do for this? We can address this this problem by choosing a convergence criteria. This is one of the method we can use, or we can also do this using a method in which we can specify the maximum number of iterations it will run. Okay, so we can do either of this or two of both of them. Now convergence criteria, okay, it is a stopping method. So it decides when to stop. So here we can put a limitation on the centroid movement. Okay, so we know each time a clustering is done, the centroid moves from this to this point. Suppose it is moving. So what we can do? We can set a threshold value here. This threshold value will be a certain percentage of the smallest distance between any two centroids. Okay, if you are having two centroids and my point is jumping from this cluster to this cluster, suppose always jumping from this cluster infinitely for each iteration. What we can do, when it jumps to this cluster, suppose this centroid moves from here to here. Okay, so we'll say that we'll set a threshold value for this centroid movement. We'll say that if it moves less than this certain value, suppose y, less than a value y, if it is moving, then this point has converged, or this k-means clustering has converged. Okay, if we are having this condition met, if this condition is met. If this condition is not met, then we'll continue doing this. Okay, so this is one of the method, convergence criteria. There is also one more method in which we can specify the maximum number of iteration it should go for. Okay, suppose we set it to 30. So 30 times it will jump, and wherever it lands on the 30th jump, we'll say this is the cluster this point belongs to. Okay, so this method can also be used. And we'll have to compare the between cluster variation and within cluster variation. So let us know what are these. Between cluster variation and within cluster variation. So suppose these are two clusters having centroids like this. Okay. So between cluster variation is cluster to cluster variation. What is the variation between a cluster to cluster? Within cluster variation is inside a cluster, what is the variation of a data point from a cluster central? Okay. So here it is, suppose we are having between cluster variation. Okay, this is not just with centroid to centroid, it will be from all the data points to other centroid. Okay. So suppose this distance, suppose this is D1 and suppose this distance is D2. Okay, so D1 here is our between cluster variation and D2 is within cluster variation. So we will have to compare both of these distance. Okay. So between cluster variation and within cluster variation we are having. So the D1 should be as large as possible. As large as possible. D2 should be as low as possible, as small as possible. Okay. D1 should be as large as possible. D2 should be as low as possible. If somehow this D1, okay, it is smaller than D2. For this point, we are finding D1 is smaller than D2. Then this data point does not belong to D2 anymore. It will jump to D1. Sorry, it will jump to this cluster. Okay, suppose this is 1, this is 2. It will jump to the 2 cluster. Okay. So this comparison is needed if D1 is greater or less than D2. Okay, the cluster or the data point will move to the other cluster. Data point moves to other cluster. If D2 is smaller than D1, then it is correct. Okay, this is what the condition should be. So we can also compare these two values to check whether this data point should remain in this the first cluster or the second cluster. Okay. Now this we are having a typical objective function here, which we should minimize. So the objective function here is sum of squared errors, SSE. Okay. So we are trying to minimize the sum of squared error, also known as variance. We are trying to minimize this variance here. So this is a minimization method, I already told you, and we are trying to minimize the within cluster variance, within cluster variance. We are trying to minimize this. Okay, and we are also trying to find this SSE, sum of squared errors. Using this only, we can find this minimization. How much this? So the sum of squared error should be as low as possible again. Okay, so let us talk about this use case. Okay, this will also be seen in the coding part. Okay, so this is clustering electric usage profiles. Now, in this use case, okay, we are going to find the daily load profiles of a single household. Okay, this is just for a single household where we're seeing this data is for single household. The date, you can see the date, the time is given. According to that, what is the power consumption? Okay, so we'll be working on this data set. Okay, and we'll be using the k-means clustering algorithm to you cluster these load profiles. Okay. Now this data set contains 2,75,000. Sorry, 20 lakhs, not 2 crore. 20,75,259 data points or this records. Okay, and it is the data between December 2006 and November 2010. 47 months data we are having here. And here we are trying to find patterns in the daily load profiles in a single household. Okay, using k-means clustering algorithm. So let me just run you through the various things which we saw here. Okay, so this is the part where we did EDA and pre-processing. So in this plot, we can see the daily load profile. Okay, it is a total of 1,456 days result we are having here. Okay, so here we can see two clear patterns. If we just see. Okay, this one. Okay, two clear patterns we can see clearly. So these patterns are the darker regions, as I just showed you. Okay, where the this curves are more concentrated. Okay, so we'll be clustering based on this. Okay, so these are all the daily load profiles for 1456 days total. Okay, next is we have done the K versus the silhouette score graph. So these are all the K values. These are all the silhouette scores. So according to our method, we should be taking this value. Okay. Somewhere around here, it comes out to be 2, but we are taking for safe measure, we are taking 3. We are taking the value of K as 3. Okay, with 3, we are getting good results. So we are taking those. Okay, so this is the after clustering. We are getting these 3 profiles majorly. This red line you can see, this blue line, and this green line. Okay, so here we found 3 unique you can say load profiles, 3 unique groups of load profiles we are seeing here. Let me take this color. So red one, you can see this is the red one, something like this we are having. Okay, then we are having blue one, and then we are having green one. Okay, so this green cluster, we can say they are the loads, okay, that maintain a steady use of energy. Okay, they are maintaining a steady use of energy. Then we are having the blue cluster, which is having a higher peak than everyone else. Okay, so we can say these are the higher peak. Maybe it is during morning, and then we see a decline in the usage rest of the period. So this decline shows in the afternoon, and we see a peak again at night. Okay, so morning, then a decline, then a peak. Then we are having red cluster. It shows days when consumption is low, but basically consumption is low throughout the day. So it can be showing means maybe during the holidays, you can see. Okay, no one is at home and all. So just few of the essential things are kept running and most of the things are not running. So we can make this inferences like this. Next, I'm also trying to validate it with this SNE graph using TSNE. Okay, so we'll also see this. So from this, we can say, from this graph, we can say ki, each color, they are representing, sorry, each point in this graph are representing a load profile. Okay, so from this 1456 load profile, we are showing this. So here we are having 1456, total of 1456 load profiles, but instead of having multiple dimension, we are just showing it in 2D. Okay. So here we can see thus different load profiles, and based on that, which we had done earlier, based on that, different colors are coming. Okay, so the points which are closer to each other, so we can say that these are clustered very well. So you can see most of the green data is lying at this region, more of the red data in this region, and blue data in this region. Okay, so we can say this has been clustered very well. Okay, so the validation is, we are finding is good here. Okay, so basically the SNE, it converts or it can transform more dimension to a 2D or 3D graph. So we have done that. Hence, we are also getting some of the overlapping points. Maybe this, if we see this in more dimension, maybe 3 dimension, we can see the differentiation. Okay, so let's go to the coding part. Okay, so this is the coding, same method we are same one we are using it. So it is the clustering electric usage profiles using k-means. Okay. So here we are having this data set 20,75,259 records we are having in between this 47 months, and we are trying to find patterns, daily load patterns in this data set again. So first of all, I have imported NumPy and pandas. Okay, pandas is used for data manipulation. NumPy is used for various arithmetic calculation and using of arithmetic functions. And also matplotlib pyplot I've used for showing the data visualization. And the style of this visualization I'm using is Seaborn. Okay. So I've loaded the data. The data is present as a text file, so I've loaded it here. Means I've given a path and I'm loading it as a CSV file. Okay. And I'm saying separator is semicolon. So basically our data are separated using semicolon. So we are using a separator semicolon. And I'm also using the column names from this list. Okay. So we are building this data set. Once this is done, we are doing the ED and pre-processing part. So here we are converting the date time to a date time format. It was not actually present as a date time format. We are converting this to a proper date time format. Okay. Once this is done, we are just plotting the daily loads. Okay, so here we are plotting this daily load. So from this, we can see that this darker regions, they show that most of this daily load profiles are, most of the daily load profiles are in this region. Okay. Once this is done, okay, we have visualized and all, we have corrected all the data. So our data now has converted from into a correct format to be used by the downstream or this ML algorithms. So the algorithm here we will be using is k-means. So let's see. So now we'll be clustering using k-means. So it is an unsupervised algorithm, which we have already discussed. Okay. So here, first of all, we have to decide how many clusters should we be taking. Okay. So here we'll be using silhouette value, silhouette scores to discuss the number of clusters. Okay. So let's do that. So I have created this silhouette graph with respect to k. So these are the silhouette scores. Silhouette scores. Okay, they can vary from -1 to +1. If -1 is the score, we can say that it has been wrongly classified or wrongly clustered. If +1, we can say it is the best cluster. Okay, so we are taking from this, the value of k we are taking is 3. Okay, as we already discussed during when we saw it in the slides. Okay, so using that k is equals to 3, we are now doing k-means clustering. We are fitting this on this data and also predicting on our data. Okay, on x is our input values. Okay, and on doing this, we are getting this 3. So let me show you this. Okay, so majorly these 3 things we are getting, these 3. Okay, let me show you here. So these 3 profiles majorly we are getting. Okay, so here we can say this, the green cluster. Okay, it contains load that maintains a steady use of energy throughout the afternoon. Okay, you can see this straight line throughout the afternoon. It maintains a steady use of power. Okay, so we can say that maybe these times the occupants are staying at home. Okay, blue clusters, we can say they are giving high peaks. They are giving high peak in the morning. Again, there is a decline here in the afternoon and then high again at night. So we can say that this pattern is a business day. Okay, this fits to a business day when occupants are leaving the work for leaving the home for work or school. So during work hours, we are seeing a dip in our, this usage. And whenever they are home, we see an increase in usage. Okay, finally, the red cluster we can see here. Red cluster shows this show when this consumption is low throughout the day. We can say throughout the day we are having a low consumption. Maybe this is due to case of holidays, or maybe only a few appliances are left on. Like generally fridge, ACs, they are left on. Maybe this time the fridge ACs are not left on, basically. Okay, so these are the clusters we have formed. Now we are trying, so now we have formed this cluster, but whether these are correct or not, we don't know. So we are trying to validate the result using the TSNE algorithm. Okay, so you can see here, one way to validate the results of a clustering algorithm is to use a form of dimension reduction method and plot the points in a 2D plane. So here we are doing this using the algorithm TSNE. Okay, but the inner workings of this algorithm cannot be explained because this is a black box model. It is also known as the full form of TSN is T-distributed stochastic neighborhood embedding. Okay, it is an unsupervised machine learning algorithm. It was developed in 2008 by Lawrence Van de Maten and Geoffrey Hinton. Okay, it is widely used in bioinformatics and generally in data science. It is used to visualize high dimensional data in 2D or 3D. Okay, so we will be using this to visualize our data, which is having more number of data points or data into a 3D data, into a 2D data. We are doing that 2D data. Okay, so we should keep in mind that this TSNE model has not yet seen our cluster. Okay, so this we are doing totally new. You can see we are just fitting transforming on X newly. So when we do this, we see a clear-cut difference between the clusters. So you can see the clusters of green clusters are this side, red clusters are this side, blue clusters are this side. Okay, so clear-cut differentiation we can see with some data points overlapping. But maybe if we saw in a greater dimension, maybe 3D, this might be also differentiable. Okay, so our if you can see the validation here. Okay, so each data point is represented with a daily load profile. Okay, we have reduced from 24 to 2 dimension. Okay, from 24 dimension we have reduced to 2 dimension. Okay, and the fact that most of the blue, red, green particles or points are closer together. We can say green particles are closer together, blue particles are all closer together, red particles are also closer together. We can say that this clustering has performed well. Okay, now in this modeling, we have represented a way to find clusters of electrical usage using K-means algorithm. We have used silhouette score to find the optimal number of clusters, and we have also used TSNE method to validate the result. Okay, once this clustering algorithm has been done, we have clustered. Now we can use those clusters to further do some further analysis. Okay, so this could also be used to extend this. We can extend this model. So this has been done just on a single household. We can extend this model to different households and find similarity between them. This can also be done to find the consumption behavior across many different households. Okay, so this can be a future project we can use this for. So yeah, friends, we are done with our K-means clustering. So yeah, so tomorrow we'll be seeing another method, which is K nearest neighbor. We'll be seeing this. It is quite similar to KNN, this K-means clustering also. Okay, so we'll be seeing this. So yeah, thank you, friends, and have a good day. We'll continue this session tomorrow at the same time. Yeah, thank you, everyone.